this is like the structure of this presentation. We start by giving just a little bit of introduction on how what we are doing, so motivation. Look at what dataset are used to train the models, model structure and fine-tuning, evaluation, and then just give a wrap-up looking at results and what we found. Okay, this work was done working with a company that wants me to develop a system that was capable of answering to customer questions, so query, in a natural language fashion. So the benefits of this you may already know, but the benefits is that it's more accessible, so we have an ease of interaction, and also we have way less information overload. So if I'm able to provide a short answer to the query that I'm trying to answer, I don't need to skim all the relevant documents that might be retrieved by our retrieval system. Okay, how do we do that? The idea is to leverage the power of large language models to generate text. The problem of large language model generate text alone is that they're not reliable. And how do we address this problem? Is by a RAG pipeline. So Retrieval-Augmented Generation. For those who don't know, Retrieval-Augmented Generation has two main blocks: the semantic search block, the one on the right side, and the generation block done by a large language model. How does it work? Is that the retrieval part might be also done with a lexical fashion, so let's say old but classical information retrieval approach. But what we're trying to do in this thesis is do a search component related to the semantics. So we want to try to catch what are all the not the keyword match, but all the contents inside the documents. And these are the two different kind of retrieval that are right now in the market, let's say. So the lexical one, you already know for sure, but it's based on keyword matching. So the problem with that is the pros is that it's very fast. But if I'm trying to search, for example, the wrong population, but in the document is expressed with different words, I'm not going to find it. And instead, with an hypothetical dense retrieval that is leveraging like embeddings. Embeddings are vector representation of a document or a query, depending on what I'm doing the embedding. And the problem with that is that it's way slower than lexical search. But on the paper, let's say, we hope that these vectors are capable of represent the semantics inside a document or the query. During the work, I split into, let's say, main categories. The one is the symmetric semantic search. So that might be useful where when I'm searching like queries among queries. So queries and documents, let's say, are almost the same length. And instead, in the asymmetric semantic search, we are dealing with short queries and longer documents. And the problem in that is that short queries are way less semantically rich of context. Instead, that it's the complete opposite looking at documents. We had like a goal that the company was using the text embedding small from OpenAI to embed both queries and documents. These are a little bit of specs. The embedding dimension is 1536. That is, as I said in the comments, it slows the search since it's not so. It's a bit embedding. So when I compute in similarities, this will impact the performance. The API call is done every time at inference, and the company asks me specifically to use local model, so that I can put on a machine and run locally without the help of API, in this case OpenAI API call. And the costs, if it has a large scale, it keeps increasing, and it's 2 cents for 1 million tokens. It's structured like this. My work was structured like this. The first 2 points are a bit mixed because I need to find both models and at the same time, and then understand how at the time this is like the research was done at the beginning of I think March 2024. So I'm like freezed at that time at all the methodologies and models that were present at the time. So how can I fine-tune these models to let them work better? And then that's the last step. Okay. First, datasets. I picked 2 datasets because finding datasets in Italian was not the best. There are not a lot of datasets available with the right license. So I found multilingual macro from Microsoft. This is a multilingual version of MS Macro, another Microsoft datasets that has 14 different languages and 39 million samples, and is structured like this. So it's structured in triplets: the query, a positive document, and a negative document. This will be useful during training because we need this structure to fine-tune these models. The models I want to show you. Okay, this is the validation and test set. I was not able to find one dataset in Italian at that time to test our models. So what we did was taking this Wikipedia entity version 2 that comes from the Wikipedia graph, where it has 4.6 million documents, and you can read the specs, but the important thing is that contains relevant judgments, and is split in test queries and validation queries. Test queries are used. We use the 400 test queries at test time, and the 767 as validation during fine-tuning. And you can see that we have 3 labels: 0 for non-relevant document, 1 for relevant document, and 2 if the document was actually the answer to the query. As an implementation design, we decided to remove this, to collapse the label 2 inside the label 1. So mark the document that are actually the answer as relevant. And I highlighted in the tables what were the original data inside the dataset, and all the other data were let's say added by me, but I need to put your attention in some of this. For example, there is an easy subsample inside the document because as already said, as an implementation choice by the company, they said to me, okay, you cannot use 4.6 million documents and embed all of them because it's too expensive. So I subsampled 150K of them, looking at the 47K that was inside the relevant judgments. So I have all the relevant, all the not relevant inside the relevant judgments, plus other documents, just to be sure that that everything works. And we have chunks. Chunks are used to fit the text inside the embedding model, the neural embedding models, since they have a limited window, and I needed to deal with that. So I created chunks of the documents that were like the not sentence splitting, but the exact length of the possible window of the model, but with an overlap, just to avoid trying to avoid the losing phrase and sentences in the way, along the way. And this is an example. Each document comes with a unique ID, with the title, with the text, and then the query is on the top right, so an ID and a text, and then the relevant judgments that relates the two tables with the query ID, the corpus, and the score related. Okay, that tells us if a document is relevant to the query or not. Okay. How do we pick models and how do we fine-tune the models, the neural models in this case? I basically not looking at business, but with neural network-based models, I looked at this massive test benchmark. At the time, there was not the multilingual version of this benchmark, but I tried to filter all the multilingual models that had different specific characteristics and that were as much as possible up on the benchmark. So it was the best as a multilingual. And as baselines, I just try to have lexical search with TF-ADF and the N25 just to have a comparison. Because the main focus of the work was trying to work with vectors, not improve the lexical part. So they told me, okay, lexical part, just keep it as with default parameters, don't work on that, just work on neural network-based models. And also I need to say that they asked me specifically for Italian. No other languages, they told me I want it to work for Italian. Okay, this is just to be on the same page. TF-IDF stands for term frequency, inverse document frequency. It has it's computed like the term frequency. You can see the formulas. I'm not going to read it, but I think everyone here knows it. And a score is associated for each term of the query and for each document inside the corpus. All the numbers are stored in inverted index during indexing, so it's very fast to retrieve, and then the score is computed. Same for VN25, that's match 25, where we have another way of compute the score, adding two parameters that are the K1 and the B, and as I said before, I left the parameters as defaults. So B is set around 0.25, and then I set K1 on the middle of the interval between 1.2 and 2.0. Okay, for those who don't know BERT, BERT stands for bidirectional encoder representation from transformer. Transformer is, let's say, very important in deep learning and board for NLP model, where it's separated between two parts that interact with each other, the encoder part and the decoder part. BERT takes the encoder part, and the BERT-based model was 12 layers of encoder, one on top of each other, and it's trained in two ways: the masked language modeling and next sentence prediction. I need to say this just for let you understand what are the differences between the model I picked after. Okay, masked language model. I sample from the input what words I want to mask, and 80% of the word I'm going to feed it inside BERT and do inference, and then at the end train predict only the selected words, and after that doing backpropagation just with the output embeddings of these words. 80% of the words are substituted with the token mask. 10% are changed with a random word, for example, pink, and I couldn't find an image, but the other 10% leave as it is. So, for example, if I pick false, it will remain false, but I try to predict false, and then I do backpropagation with that. More than that, it's trained on next sentence prediction. What is next sentence prediction? It's like we have two sentences, and I want to know if the two sentences are next to each other in a text. So basically, just related. They are talking about the same topic. It's structured in this way. So between the two sentences, there is the separation token. And then at the beginning, there is this is important, the CLS token that stands for classification and the classification of class. And what I'm doing is that I'm doing inference with this input and trying to attaching on top of the embedding of the CLS token for classification a linear layer and then predict and try to say I need to have a corpus with the sentences and the scores about the sentences, and then doing that propagation if the sentences were near to each other or not. I hope I've been clear. When we have BERT, we want to build an embedding of, let's say, of a text, okay? And a good way of training these models to do so is by using sentence BERT. That is just a way to train, basically a way to change the parameters of BERT. And it's leveraging Semism network. Semism network is just a fancy way to say that these two networks are the same network, so same parameters. And what I'm trying to do is that I fit the two models with the two inference separated. I fit the two models with the two sentences. After that, I do a pooling layer. Pooling layer is basically just choose how I pick my embedding. So two very common way are using the CLS token, or another one is use the element-wise mean of the entries of all the vectors containing the sentence input. After that, I use a similarity function that can be cosine similarity or dot product that are different because cosine similarity is a normalized version of dot product. So cosine similarity is between -1 and 1. And dot product, you cannot control the dot product. The three models I picked are a language agnostic BERT sentence embedding. This is from Google AI. It claims to have 109 languages supported. When someone goes and look at actually the corpus used to train, there are very low resource languages, so it's a bit more unpredictable the output. For example, I just inserted some of the specific characteristics of this model to compare the three after CLS token pooling, as I said before. Half of the dimension of the embedding for this model, looking at OpenAI text embedding 3 small, and 12 layers of transformer. So built on BERT base. Multilingual E5 text embedding, we picked the large version. I just it's from Microsoft, and I just show you the differences. The window, maybe I forgot the window in the last one. The window was 256. This is doubled, but I need to add the prefix. For example, query for the query and document for the document. And I have a larger embedding dimension and mean pooling, and it's pre-trained. It's initialized on a different network that is a BERT with 24 layers, but it's called Roberta because it's trained in a different way, and also it's XLM is another way of training on top of Roberta. Roberta. And Roberta, for example, use a dynamic masking instead of BERT. Instead, the BERT training masking was the same on all epochs. Roberta is not like that. So the masking is done differently every time on the epochs. And XLM is basically the addition during training of cross-language. So corpus aligned for translation, basically. So and they also used that kind of data set to train this kind of model. Last one is basically the same initialization as before, different pooling, but same embedding dimension. So we are talking about the same, but almost the same model, but we have a very, very large window. So I picked this model to see how the windows were affecting actually the performance at the end. And okay. I'll explain you the idea before going a little bit deep on details. The idea was to not waste too much resources by training the model. Pretrained model in this case are or LaBSE and all the models I cited before, but try to reduce the number of parameters changed. And I found out in a survey that this was at the time this was a good way to do so. And the idea behind that is that the model is we assume that the model is capable of doing a good embedding, relatively good embedding when he has enough context. So when in a document where the context is way bigger, the embedding we assume that is way better than in a query where the query has way less context, way less semantic load inside. So we apply an adapter on top of the query embedding. That adapter is like the initial idea was a 2-layer neural network, so a multi-layer perception or just 2 layers. But to reduce again parameters, they thought, okay, start with a linear layer and then see if it performs well, and then if we are able to do what we want, leave it like this, or insert to add a layer in this adapter, so from 1 to 2. And just a bit of training specifics. We use AWS to train on A2 machine with G5X large. This G5X large was picked for a reason, because we wanted the GPU to be an NVIDIA of A10G. In this way, it supports a different data type that is B1216 that is used to speed up the training, because it has less precision that TensorFlow with 32 bits. So the result is that the training was sped up like by 3 times, by a factor of 3, having this change. And the loss was a triplet loss, as I mentioned you before, because we have the 3 embeddings, so the query, the positive document, and the negative document. And then after we do backpropagation with the loss. That the loss is trying to maximize the distance between the query embedding and the negative document embedding, and alongside with the minimization of the query embedding and the positive embedding. Fine-tuning hyperparameters. Some of them are very basic. So add them with weight decay, fixed decay, batch size. They also, in this case, they told me don't change too much parameters, so we are gonna waste time. So max possible for the model. We reduced the data, so not 39 million samples, not just 5 million. And the validation were done every epoch only 5 times with a subset of the validation set. This is a plot just to show the warm-up of the learning rate, and then the cosine annealing part to let the model ends its learning better than by leaving the learning rate stable. At the end, you can see in this case that only the last model has a nonlinear adapter. The nonlinear adapter is because no linear one was improving, so we tried different configuration, and the best is still not the best, let's say. Okay, evaluation. We used a vector database called Weaviate to index the documents, and we perform both exact search and HNSW search. HNSW search is a approximately nearest neighbor search done to speed up the semantic search. Because if I needed to compute a full KNN on a lot of documents, it makes no sense. It makes sense, but it's too slow. And basically, that index is takes inspiration of looking at two things: skip lists and small navigable words that are graphs. Skip lists are built as is a probabilistic data structure that is built by inserting in an ordered way. In this case, we are only numbers, but then it became scores in distances, not scores. And how do I perform search in this data structure? I start from this is order, so I start from the top left, and then I search looking at the right values. What are if the right value, the immediate most right value I found is greater. If it is, I stop and I go down a layer, because each layer has, here is evident, but each layer has more points. And so if I need to perform the search on the last layer, only on the last layer, I will take more time. And so I don't find it on the first, on the S5, so I go on the S4. I found, let's say I want to find like 40. Okay, I go to 17. 17 on this top left has plus infinity, so it's greater than 40, so I go down. And then I do like this path until I found, and I'm in the last layer, and I found near to the nearest left value, the immediate most left rightmost value. So I know that my my number that was 40 is near to 39 and 44. And so I, let's say, found the two nearest elements in the list. As navigable small words are basically a graph constructed starting by, it has two types of, in this case, it has two types of connection, the short and long range connection to, let's say, traverse the graph in less time. And I start from an entry point, and in this case, I do a grid search, but it will not be the case on the actual index I will talk to you after. And I find traversing the graph the nearest neighbor inside the points of the graph. How do we mix these two data structures? We build hierarchical navigable small words. And how do I do it? As I said before, the skip list is a probabilistic data structure. I forgot to say that the insertion is random, and this randomness is sampled in a probabilistic function that is skewed to the bottom. So it's more likely that I pick bottom layers instead of top layers. So and also the fact that when I insert on a top layer, I need to put the data point in all the layers under it. And let's say the idea is that on the top layer I have longer connection. So I traverse my my data point and go near to a document by starting from the embedding of a query by looking at the first layer, and then I go down. When I go down, I start searching again, but I assume I'm starting from a better point than before, because I traverse the top layer graph, and then I found the nearest neighbor on the top layer graph. And during indexing, this has two important parameters, the M parameters and the EF construction parameters. The M parameters are the number of links when I insert a new document inside the data structures that are allowed to have, that a document has allowed to have with its neighbors. And the EF construction is how many neighbors I look when I insert something to speed up the indexing. And this affects both time and accuracy, because as I told before, it's an approximate nearest neighbor algorithm, not an exact one. We explored a lot of metrics, but the two mains are recall at K. So the recall looking only at first K documents retrieved by the system. But the problem with the recall is that it doesn't take into account where the position of the relevant document. So if it's retrieved on first position or third position, it's exactly the same contribution to the metric. So we try to compute normalized discounted cumulative gain that let's say have a discount on a top document as a higher score than a bottom one. So if I retrieve in a logarithm scale, so if I retrieve the relevant document in the first position, I'm going to have 1 over logarithms in base 2 of 2, so 1. But if I have on the 10th position, this grows, and so I have a lower score. And this is just a slide to see what was the implementation. Elasticsearch for the count-based models. At the time, I didn't know that I could have performed vector search with Elasticsearch. So they told me to explore with Weaviate, the vector database I told you before. And this is just a recap slide with the addition of the fact that when I was comparing two models, I performed also a statistical test to see if the metrics retrieved for each of the queries that were inside the test were actually, I had a statistical difference between the two vector of values that I output. And we picked the Wilcoxon sign rank test because at the initial stage, we tried a pair t-test that is more classical way to test. But we needed to remove the assumption of normal distribution of the data. So because the data was a small data set. This is just a time recipe, but computed with the scripts. So in this case, I need to put the attention on the fact that text embedding too small requires an API, so the API depends on the network. And these times are computed by using my local computer that has a small but has a GPU. So I have the time that you can see. And the spoiler is that the underlined one is actually the one that performed better. And perform better also than OpenAI model. So this is like a bar plot. I need you to focus on the not gray color. So for example, in this case, LaBSE has improved with the adapter by his, let's say, brother without it. And same with Multilingual 5. And but Multilingual 5 has also had a statistical improvement over the same computation, but with the text embeddings mode from OpenAI. So it seems like in this task, looking at Italian and with this kind of fine-tuning with unfortunately translated dataset, it performed good enough. We are reaching the end of the presentation, and as a summarization, 2 of the 3 models worked well, and it was, I labeled it as a cost-effective solution because it has only the training, the initial fine tuning, and then since they wanted the model to be in a local, they will run on their machine, and the inference time is lower, even if there is this thing about the network for the API call. And since it has a lot of limitation, there is a lot of future works. For example, I didn't evaluate with the semantic search system was not introduced inside an actual RAG pipeline, so we don't have user-centered metrics. And the data set was not the best, as I said before. And since they didn't provide me with like domain-specific data set, it would be useful to try and fine-tune the model on a domain-specific to see if actually a good data set can improve the work, the performance. And we didn't explore the ranking part of query writing, because query writing in particular, because we don't want to rely on LLMs on the first part. And like different fine-tuning technique might be explored in the case. And thank you.